Yeah, welcome back. So now we're going to continue to our second video. Here I'm going to give you some mathematical tools we need for solving the continuous type problem. In particular, I need to remind yourself about integration by parts and to introduce the envelope theorem to you. Okay, so let's continue. Let's start from the easier one. Suppose you have a function that is a product of two functions u and v. If we do the first order derivative for these two functions, okay, I mean one function, yeah, then we get the product rule, u v prime plus u prime v, okay? And then if we now do an integration and make things back, for the left hand side, it will become uv again, okay? Integration of the differentiation is the original thing. But here, suppose the range is from a to b, now we need to plug in a and b here. And for the other two things, yeah, it's just we keep them the same and do an integration from a to b, or from a to b, nothing special. And now, let's focus on this term. This term, if we put at the left hand side, and take this term to the right hand side, we can see that this integral can be found by doing first these two plug-ins and then another integral. Okay, this is what we call integration by parts. Okay, and while we have this complete formula, we also have an easier way to memorize it. Okay, the way to do that is say u dv equals uv minus v du. Okay, this is how people may do when they want to memorize this integration by part formula. One thing to remind you is that when we have this, if we do a definite integral, we need to specify bounds. Okay, and here we need to plug in bounds. For example, from a to b. Yeah, integration by parts. We're going to use that later. Okay, now let's consider something new. It's called envelope theorem. Okay, the name is not very important, so yeah, anyway. So let's see what this theorem wants to tell us. Suppose you have a problem. Okay, here you have two parameters in this function, and you are maximizing this function with respect to x. In this case, certainly we say x and theta are somewhat different. X is the variable, and the theta is the parameter. In general, they can be multi-dimensional. I mean, a lot of variables, a lot of parameters. But here, let's assume it's a scalar, it's a scalar. In this case, we can say that we can find the optimal solution for the function for each given theta. Okay? I mean, suppose we can do that. In that case, we say x star of theta is the optimal solution given theta. This should be a function of theta because when theta changes, the problem becomes different and the optimal solution may become different. If we plug in this optimal solution back to the original problem, we will get, we call it f star of theta as the optimized objective value. Okay? And the thing we want to ask is, how does theta change our optimized objective value? Okay? Because you know when theta becomes different, f star of theta will also become different. Our question is, how is this change measured by this first order derivative? So certainly we assume all those things are differentiable. Okay? So let's see an example about what's the idea here. Suppose your f function is this guy. Okay? Theta minus x minus theta squared. Then your optimal solution would be theta. Okay, first order condition, and this is a concave function. And then if you plug in theta back, cancel, and then you get theta as the optimized objective value. Okay, and then the desired quantity you want is 1. Yeah, nothing special. So you may feel that, yeah, what's special here? Okay, the thing is that we want to have a formula to help us to calculate this quantity. Okay. I want to find a formula so that I don't need to carry out the calculation here. In particular, I hope I do not need to plug in the optimal solution and then do differentiation. I want some kind of formula to do that. So let's see what's that. The theorem is indeed giving us a formula. So the quantity we want can be found in the following way. Here, I need to first find the optimal solution, plug in, and then do the differentiation. Here, I'm saying that I can reverse the order. So I'm going to first find the original problem, do the differentiation. Okay, here it should be with respect to theta, right? And after this, plug in the optimal solution. Okay, so the order may be reversed. Find the optimal solution, do the differentiation, or do the differentiation and then plug in the optimal solution. Yeah, let's see why they are the same. So we want to do this left-hand side. This is exactly, This is exactly what we need to do if we write the original form. Okay, just the original definition. And then when I want to do this differentiation, I know how to do that from my calculus course. Okay, this is a two-variable function. So I need to do the differentiation for the first variable and then plus the differentiation I get from the second variable. And for the first variable, I need to apply the chain rule. So I'm going to do this. First, I need to differentiate the function with respect to the first parameter. And then times the chain rule. What I should get from the chain rule. Okay? And then I need to do the same thing for the second variable. The good news here is that the second variable itself, if we do this part again, it gets to 1. So we don't have that term. Okay, so this is something I want. But I need to do something more. If I only have this, then you can see, for example, here. After differentiation, you get x somewhere, right? But in the original thing, there should be no x. This tells us that we need to somehow plug in x as what we have in the first parameter. Okay? Because x has been determined by theta. So after this total differential, we need to plug in x as what it is determined by theta. If I do this, then things will be very interesting, because when I do the differentiation, first order derivative, and then plug in the optimal solution, okay, optimal solution, I know if x star is an optimal solution, this plug-in must give me 0, right? Because I have the favorite first order condition. Then this part I don't care, because they together will get me 0, right? So after I do this plug-in, I get only the last term. I do the differentiation first, and then plug in the optimal solution. Indeed, this is exactly what we want. Okay? So that's how I get this formula. So here, we're almost done. Let me show you how may we is removed. How may we apply the rule to our original example. Okay, this is our original problem. When we want to do a maximization, blah blah blah, this is what we get. Here, if I want to apply the formula, it will be I first do the differentiation and then plug in the optimal solution. Here, optimal solution is theta. First order derivative, I get 1 minus 2x minus theta plus. Okay, and then plug in. I get exactly 1. Okay, so at least for this example, our envelope theorem works. So I'm not going to give you more examples. I mean, to derive the result for more examples. But if you want, or I encourage you to consider one more example. Okay, for those non-negative x, let's consider this example, this function f as again a concave function on this region. Yeah, you may be able to go through the two different directions and eventually get one single result. Yeah, and that's envelope theorem, a formula for you to find this quantity without finding the optimal solution and plugging back and whatever. Okay, we're going to use that later. Thank you.